Okay, today we're going to be looking at section 5.2. This is properties of functions. Objectives are as follows: determine intervals of monotonicity of a given function, determine maximum and minimum values of curves from a given graph. We're going to determine the average rate of change from an explicit defined function, determine average rate of change of a function from a graph, determine the symmetry of functions and equations, and then use average rate of change to solve applications. This section, I do believe, does a very good job of explaining things, so I do recommend you go through and look at the information. So here are some properties. First, they show us y-axis symmetry. This is also called even, okay? Even functions. I will also try to show you some, I guess, indication of the type of symmetry that a graph might have based on the exponent. But this is very good. The f of negative x is equal to f of x. I'm going to draw all of these out for you once we begin the practice examples in Hawks. But they're showing you a parabola. They show a red side and a blue side. If you flip it across the y-axis, and what happens is you take some point and you change the x value negative. That's what they mean by negative f of x. If it flips across the y-axis and it's a good match or perfect match, then it's called even. Here's an example of how to solve that. You take a function, you replace the f of x with the negative f of negative x everywhere you have an x, and then if the resulting equation matches the original, then the function is even. One thing that might help you is if you look at the largest exponent. The largest exponent is an 8, which is an even number. So that usually, and doesn't mean always, okay, but that kind of indicates the type of symmetry a graph might have. So I would assume that this was leaning toward even, and then you solve it and you prove it. So don't always think that just because you have an even number is going to be even. Sometimes it doesn't work out because of translations and shifts, but that's just one thing to look out for. Then we have origin symmetry, which is also odd, and what that does is we replace both x and y negative. That will be the same as flipping this across the x and then across the y. I'm doing both of them. And then you replace the outer function and the inner function with the negative. And I'll show these as we begin to work them out. Here are all the symmetries listed. You have y-axis symmetry, which is also even. You just replace x with the negative x. This is what happens. You have x-axis symmetry. Doesn't have a special name. You just replace positive y with a negative y, or just change the sign, because if it was negative you would make it positive. And then you have origin. You replace both x and y with a negative, or change the signs of both x and y. Here's some examples and some illustrations that they go through. I also want to mention that if you're unfamiliar with symmetry, or it's been a while, we have these special names. We have odd functions, and then we have even functions. This is referring to the type of symmetry. Usually when we talk about numbers, if a number is even, it's not odd, and vice versa. But you can have a function that is both even and odd, which means it has both y-axis symmetry and it has origin symmetry. That's what odd means. So don't think just because it's even that it cannot be odd, or vice versa. It can be both. So here are those examples. This one just has x-axis symmetry. You see if you flip it across the x-axis visually with your eyes. Here are some graphics, and they tell you the type of symmetry they have. Now this is intervals of monotonicity. Basically, it tells you if a graph is increasing, decreasing, or constant. The way you read a graph is the same way that you read a paragraph or a statement or a sentence. You start on the left and you go to the right. So if everybody's going left to right, then you'll understand this definition. So increasing, if you have 2 points, x1, x2, and it's telling you x1 is smaller than x2, which means you're going left to right. That's what this is saying. And if the y value, the first y value, is smaller than the second y value, then that means that function was going up. And then similarly, decreasing, you have the two x values in same order. x1 is smaller than x2, so you're going left to right. And then if the first y value is bigger, which means it was going down left to right, then it would be decreasing. And then you have constant interval. If you have two different x values and the y values are the same. All right, so here, if you see how, I know that arrow is pointing up that way, but as you go left to right, this is going down. So we would say decreasing until you get to 2, and then it starts increasing all the way to infinity. So they're showing you that here. From the left side of the graph, you describe the intervals of monotonicity or decreasing, increasing intervals based on the x-axis alone, where it starts and where it stops. So since that arrow is pointing, that means it's going all the way to negative infinity and decreasing until you get to this point, -2, which is what they're showing here. And then at, not -2, at +2. And then at +2, is going up or increasing all the way to infinity. So that's what this means. And then we have some modeling. Good examples always to look over those. And then we have local minimum, local maximum, and different extrema. So notice how this graph has a low spot, which we would call a valley, a dip. That is called a minimum point. Local minimum, absolute minimum if it's the lowest point on the graph. Okay, but they all can be local minimums. And then we have another image. Notice how it goes up to a point. It's increasing, or a hill, mountaintop. High point would be a local maximum. They're showing you where it is and what it is. And then here's some examples that kind of go over. This would be what we would call an absolute minimum. It's the absolute lowest point. This is a local maximum. This is a local minimum. This graph will not have an absolute maximum. As indicated, these arrows continue to go up forever. So they're approaching positive infinity, but infinity is not a number, and you never actually reach infinity. You're always moving towards infinity. So there's no maximum, no absolute maximum, but we can say there's an absolute minimum because there's no point on this graph lower than this point here. And then average rate of change, if you don't know that term or you're not familiar with it, it is just another way of saying slope, rise over run. You do your y1 or y2 minus y1 over x2 minus x1. You have 2 points. You subtract the difference in the y's on the top and the difference in the x's on the bottom. That will give you your slope or your average rate of change. Basically, you need 2 points. And here's some examples here. With this line, it's not constant. It's increasing, but if you do the rate of change between these 2 points, is going to be different from these two. It might be different from those two. So we'll be looking at that. And we'll work some examples like that. So here we go, average rate of change, showing you the slope formula, the change in the f or the y values over the change in the x values. That's what this little delta symbol is. The triangle is called delta. Just means change or the difference. This term secant line specifically means just the line between 2 points. You're going to use 2 points to come up with that line. So the secant doesn't mean anything special, just 2 points. 2 points when you think of that term secant. And then we have some examples that they're showing you how to find the average rate of change. And this is called the difference quotient. It used to be a calculus concept, but it wants you to, I guess, start using it here with algebra. And this is just another way of finding the average rate of change. It's telling you differentiation and the difference quotient are the same thing in calculus, but a little bit more challenging here, but this is really a good concept to cover, and we'll touch on that when we see it in the examples. And then here's one final example talking about average rate of change. All right, with that, we're going to go ahead and jump over to Hawks and begin working.